We're going to look at Bayes' theorem. I'm going to show you three different ways that you can use to solve it. And I think the best way to introduce what Bayes' theorem is through an example. So let's start with this question. The probability that a woman aged 40 to 50 in a particular region has breast cancer is 0.8%. If a woman has breast cancer, the probability is 90% that she will have a positive mammogram. If a woman does not have breast cancer, the probability is 7% that she will still have a positive mammogram. Imagine a woman who has a positive mammogram. What is the probability that she has breast cancer? So this question is a very involved word problem. You can see there's a lot of probabilities in there. And I'll explain why exactly it fits the framework for using this procedure. But before we do that, I just want you to read through the problem, maybe pause the video, think about it a little bit, and just make a guess. Based on this information, what would you estimate the answer to this problem is? Don't calculate anything, just give an estimate. Okay, so I want you to keep that estimate in mind and we'll go through and solve it, and then you can go back and kind of compare to what you thought. Now, I really like these type of problems specifically because they really apply to the real world, because we all have medical procedures and we get results and we have to be able to interpret what those results are. Okay, so let's look at one way we can think about solving this type of problem. So what I did here is I just translated into what's called natural frequencies, because if you look at how the original problem is worded, the 0.8%, the 7%, the 90%, might make it a little confusing to kind of understand what's going on. But if you look at that 0.8%, if I changed it to 8 out of every 1,000, that makes it a little bit more tangible. And I think that's easier to understand what we mean by 0.8%. So out of every 1,000 women, 8 of them in that particular region are going to have breast cancer. Of those 8 women, 7 will have a positive mammogram. So again, just going back to how it was written before, it said that there's a 90% chance that the people who have breast cancer have a positive mammogram. Okay, so the 7 out of 8, there's a little bit of estimating going on, but if you take 90% of those 8 people, it's about 7.2. So we'll just say 7 because we're talking about people. We need a whole number. So 7 will have a positive mammogram. Okay, now of the remaining 992, so where did that number come from? Well, remember, we originally started with 1,000 in our population. We said 8 of them had breast cancer, so the remaining won't have it. So that's where the 992 came from. And then we say that about 70 have a positive mammogram. Going back to the percent, it said 7% who don't have it will test positive. So there's, some sort of error with the test. So 7%, that will give us 70. Again, a little bit of an estimate. Okay, now same question. Imagine you have a sample of women who we know tested positive. So that's something that's known to us. And now we want to know what's the probability that that person actually has breast cancer. Again, very much could be a real life situation. If you're an older woman like me, you have to have a mammogram every year, and there is a chance that you can get a false positive. So we're saying if you test positive, what's the chance that you really have breast cancer? So I just rewrote the problem here so that we still have it in front of us. So let's think about how to solve that. First thing I'm going to figure out is the total number of people who tested positive. Okay, so that is really in our question here. We said 7 who have breast cancer tested positive, and then 70 who don't have it tested positive. So if we just add those together, we get 77 people tested positive. Now, here's the question that they're asking us, because we know they tested positive. So that's our sample, 77. Out of those 77, what's the probability that they have breast cancer? Well, we said 7 of them have breast cancer out of those 77. So 7 out of 77, which equates to about 9.1%. So go back to the guess that you had. Likely you had a much higher answer. I know I certainly did before I calculated. I'm thinking there's a pretty, it's not completely accurate, but it's in the 90%, pretty, decently accurate. But if you think about what this results mean, it's kind of mind blowing because you test positive, but there's only a 9% chance that you actually have breast cancer. So I like to use this as an example because anytime you have some kind of test, we know there's some kind of error with it. And it can help kind of put your mind at ease because even though you tested positive, it's always good to get another test, get a second opinion, make sure that that's accurate before you start worrying. So I thought that was kind of crazy when I saw that answer. Now, what's interesting is the way that it was first given with the percents. There was a study done, and I gave like a snippet from it here, that doctors are actually really bad at interpreting test results like that. And they found that if you translate it to the way that we did natural frequencies, it jumped up. So originally only 10% of the doctors correctly interpreted the probabilities. But when they translated it to natural frequencies, 46%, which is still not great, but a lot better. And I will include the link to that study in case you're interested in reading about it. Okay, so let's look at one other problem. This one we're actually going to do in 3 different ways. So the first way, we'll do it the same way we just did, and then I'll show you 2 other ways we could do it. Okay, so you can see it's like a similar situation where there's a lot of probabilities. Here we're talking about a population where you either do drugs or you don't. So 1% of the population is a drug user. We're going to randomly select someone to test for drug use. We know that the test is 98% reliable. Okay, so a little bit more reliable than the last example. So, and it just explains what that means. If you use drugs, you're identified as a drug user 98% of the time. And if you don't, you're identified as a non-user 98% of the time. So if the person we select at random tests positive, what's the probability that they actually use drugs? Okay, so first step, just to do it the first way, I'm going to translate it like we did last time into natural frequencies. Okay, so I kind of kept the same problem, but put it with numbers instead of percents. So suppose we have a large population, 100 out of every 10,000 are drug users. And then you can see I just rewrote the 98% reliability means that 98 out of 100 are identified as drug users and 198 of the remaining 9,900. So again, thinking our population is 10,000, that's where that number came from. And then 98% of that, 198. The 2% of that. And same question as before. Okay, so we answer it the same kind of way. We get the total 98 plus 198. So that comes from, in the parentheses, we said 98 of the users are identified as drug users and 198 of the non-users. So how many people are identified total? Just add those up and add to that total. How many are drug users? Well, it's the 98. So 98 out of that total, which was 296, which will give us 33%. So even with a test that was 98% reliable, there's still a pretty low chance that the result was accurate. Okay, now I want to show you, I'm going to keep the same question. I'm just going to show you a different way to solve it. And this is, if you took a Prob and Stats course, this is probably the formula that you learned. And it's a little ugly looking. I know in the past I have taught this And I can explain, I can make it so that you can easily solve these problems with no understanding whatsoever. So that's why I liked that first method better, because I think it really leads to understanding. But the way that Bayes' theorem works is you have a sample space, and it's split up into these regions. And so if you look in this picture, S is for sample space, and I split it into S1 through S6. So 6 different regions, and they're all, we call them mutually exclusive. And all that means is that there's no overlap. So like S1 is completely separate from S2, S3, S4, S5, and S6. And we can say the same for all of them. So it's basically like carving up the sample space so that there's no overlap. So that's all that those first 2 lines say. And then the second part, where it says S1 plus S2 plus Sn equals S, just means that it's the whole sample space. So there's no other set within that space. So if you think to the example, we said there's drug users and non-drug users. There's no other possibility, right? You're either a drug user or you're not a drug user. So it would be, here's the sample space of people in that population, and then they fit into one of those 2 categories. So those 2 categories are mutually exclusive because you can't be a drug user and not a drug user, so they're separate from each other, and they also make up the entire population. And then you have some other event, and you want to find the probability. So this line just means given. So the probability that one of the S's happen, given we know this other event A happens. Okay, and this is the messy looking formula. I'll show you just with that example how the formula kind of translates. So this is the same question we saw before. I just wrote it over there. And I just wrote out some of the probabilities. So I kind of pulled them from the problem. So what's the probability that you do drugs? 1%. So 0.01, just writing it as a decimal. So if you do drugs is 1%, the probability you don't do drugs is 99%, because again, those are the only 2 possibilities, and they have to add to 100%. Okay, the third line, probability that I wrote yes for test positive. So you tested positive given you're a drug user. Well, that's what they told us with the 98% reliability. So the probability that you tested positive given you're a drug user is 98% or 0.98. The probability that you tested positive given you're not a drug user. Now, they didn't give us that, but they told us that 98% of the time a non-user will be identified as a non-user. So to find the probability that they will be identified as a user will just be 1 minus that 0.98. So that'll give us 0.02. We're looking for the probability that you do drugs given you tested positive, because if you read through the problem, the last line, that's what they asked, right? We know you tested positive, so that's a given, and we want to know what's the probability you actually use drugs. So the bottom line here is where I'm plugging into the formula. Let me move that a little bit. Okay. So the way I used to explain it is we're looking for the probability of D given Y. So the top of the fraction there, you take the probability of the first one, so probability D, and then you multiply it by reversing Y given D instead of D given Y. That's the top. Take those 2, repeat it on the bottom, plus, and then basically the same thing, but wherever you see the D's, change them to not D's, because that's like the second S in your sample space, using drugs and not using drugs. And then you just take all those probabilities that you have up there and plug them in, because you have everything you need, and then calculate it out, and we get that same 33%. Okay, again, you can see it's kind of mindless because you don't quite understand what you're doing. You're just plugging into a formula. So I don't love this way, but it is in textbooks, so just wanted to explain. There is one other way that's also kind of neat, which would be using a tree diagram. So I'll take that same example, so we already know the answer and how it works out, and we can kind of set up a tree diagram again, thinking of, we split into drug users versus not drug users. So those percents came right from the problem. 1% uses drugs, 99% don't. So that's the first kind of split. Then within each of those groups, you can either test positive or negative. So that's the second part that I wrote. So if you're a drug user, you're going to test positive 98% of the time, which means the remaining 2% you test negative. If you're not a drug user, you test positive 2%, and the remaining 98% you test negative. So that's kind of setting up the tree diagram. And then you can use the tree diagram to figure out different probabilities. So the probabilities I was looking for here, the probability that you take drugs and test positive, you can just kind of follow that line in the tree. So it's just the probability you take drugs, 0.01, and usually in it's a little bit of a simplification, but usually and means multiply. 0.98, so we just multiply those together, and then the same down here, the probability you don't take drugs and you test positive, you can see it's that 0.99 times the 0.02. Okay, and then finally, to answer our question, the probability that you take drugs and test positive, well, that's the top answer that we had up there, 0.01 times 0.98. And then out of the probability that you test positive. So there's two cases to test positive. It could be that you take drugs and you test positive, or you don't take drugs and you test positive. So that's why I wrote it as an or statement there. And then, or, again, it's a bit of a simplification, but usually or means plus when you're talking about probability. So those two, we have both of those. And then you can see I just filled in. Now this is equivalent to what I just showed you on the last, but I think the tree diagram kind of helps you understand a little bit about where those numbers are coming from. So I do like the visual a little bit better than just trying to plug into the formula. Okay, so you can use any of those three methods. You're basically doing the same calculation. It's just a matter of helping you understand either with the visual or with the natural frequencies to kind of give you a better understanding of what these types of problems mean.